Prison inside water, stuck between the bars. Strong hands gone, you can never go back. Struggle to survive, and you're still alive. Even if you've been misled, tell your dreams again. Carry on. Even if you can't forget, take a quick look at some of your regrets. Laying up the bricks now, as if you need a wall. Stop the fall. Some bones are not even broken yet. So push yourself through without your regret. Even if you've been misled, tell your dreams again. Carry on. Even if you can't forget, take a quick look at some of your regrets. wherever you go, just be honest as you know it. Some people will tell you not to. I will tell you, just do the right thing. I believe in you. This is real. You can't turn it off.
What's up, guys? How are you doing this Monday morning? It's a brand new year, brand new time. Uh, Hopefully everybody's going to get started off on the right track. Um, I myself am not doing bad. I got a big project we're working on to get done for Friday for pro fire safety. Get them done and out. Uh, it's been a it's been one that's kind of been pushed to the back, and Devlin's been very accommodating. So we'll get him taken care of and out, and basically just go from there. Got a couple other uh, projects going on. Um, we are we are doing a lot of stuff this year. This year is going to be the year. We're going to make it the year. We're going to continue doing coffee and cuts. We've got our uh, DIY CNC course coming out. We've got Cross CNC Signworks going as usual, and we're pushing Cerberus CNC. So all that on top of getting organized. We're gonna get organized and we're gonna get this thing out. We're gonna have everything's gonna be happening out in the shops and go from there. Um, so some things that I've been asked. One of the cool PMs that I got was being asked um, what controllers do I have? Um, so I have a bunch of different machines in the shop. I have 3D printers and I have vinyl cutters and mills and lathes and plasmas and routers and lasers and I have a gantry system for uh, a paint system. Um, you know, stuff of that nature. Each and every one of those has its own controller and pluses and minuses. Some of the best controllers, I'll tell you right now, the best controller that I am using in the shop right now is on the CNC for newbies. It is a Gecko G540 using a UC CNC plugin. And what makes that so nice is there's a USB wireless pendant that you can use with it. The interface is a lot like Mach 3, but I think it's more user-friendly, more intuitive. There aren't as many options on the screen set. It's pretty straightforward, and it's not as cluttered as Mach 3. That's just my take on it. For ease of use in learning, I have a Demon controller and an X controller, which are both Gerbil-based controllers. Those are pretty much your run-of-the-mill, like basic introductory, don't do a whole lot, but they're useful. They're really good to get people started in learning. So that's kind of the tiers of controllers. I would say UC CNC with a Gecko G540 and a UC 100. Then the Mach 3 with I have a home built servo system on the one, and I have a home built stepper system on the other. actually, I have two home-built stepper systems. One stepper system is on a CNC lathe, one's on a mill. Then I have a servo system on a mill. They're great, but they're very hard to set up initially. And then bottom tiers are my Demon and X controller, not the controllers themselves, but the Gerbil firmware utilizing the Arduino. It makes it a very elementary controller. Okay, so if you want to do a lot of CNC programming with macros and stuff like that, that ain't happening. You know, you'll have to write the macro in Excel or handwrite it and then paste it into the actual code. So they don't recognize very many macros. You know, so take that for what it's worth. That's my 2 cents. So today we're going to talk about CNC spoil boards, and we're going to get into a little bit of G-code reading. I've had a lot of people ask me about that as pertaining to CNC routers and programming those. So spoil boards. What is a spoil board? A spoil board is a base that you use on a router or mill or anything like that. It's basically just a sacrificial board or plate that you put on, and you can use it as a fixture plate, you can use it as a mounting plate, so on and so forth. So let's go here. Okay, these are different spoil boards. This is for an Avid CNC. There we go. All right. This is like an IRC, IR2C. This is like a Shark or an Axiom. This Avid CNC is just a MDF top bolted to an extrusion system underneath, and nothing really of merit on that. It's simple, it's functional, and it gets the job done. This one actually utilizes a T-track system on top of an MDF slab. Same here. This is an aluminum extrusion bed with T-tracks. These have different clamping capabilities. The Avid CNC has hold clamps for large panels. They have bolt mounts for different clamping of lower material, thinner material, not lower. This one is basically it's just a screw together, quick fixture. This one is a nutsert spoil board where you basically run bolts into these holes to hold clamps and fixtures in place and whatnot. You can see it in use here. This one, same setup, but different clamping systems, different offsets for clamping systems. Uh, there's always a plus and a minus to spoil boards. This one has uh, a screw system with a dog hole system. So you put these bench dogs in there, and that gives you kind of like a zero plane uh, for X, Y, and then you zero off the top. It has the push clamps, like you could fit a Festool push clamp set in there. Those holes are usually 20 millimeters. Festool kind of paved the way on a 20 millimeter dog hole system. I'm not quite sure why that took off the way that it did, if it was just marketing on Festool's part, but it is what it is. A lot of people get hung up on spoil boards, and I can and I can't understand why. So for the CNC for Newbies machine, I'm using a simple Avid style spoil board, single sheet of it says it's 4x8 MDF, but MDF is usually an inch oversized. So CNC for Newbies machine has 50 inches by 99 inches of travel, and it has spacing 17 and a half, 35, and 53 are the cross braces, and then zero, the 0 point on each end. So my spoil board's not quite going to cover the whole travel of the machine, and I'm all right with that because I'm not really going to do much. What I will do is put covers over the edge to protect the linear bearings, and then mount on the spoil board. So what I'm actually going to do is overhang my spoil board to the front and to the sides. So I'm actually going to go a ½ inch off of home, and I'm going to go a ½ inch off of X home, and I'm going to go 1 inch off of XY, and I'm going to line my spoil board up. And then wherever the back end of that spoil board is, I'm actually going to make another cross brace, and that will allow me to put the back end down. So I'll have some more bracing there. It's nothing major, nothing spectacular, but it needs to be done. So once I get that all screwed down and everything, we'll actually have a surface program written, and we'll surface the whole back end and go from there. And I'm actually doing that right now. So take that for what it's worth, and we'll go from there. The way that I'm actually making my spoil board is I'm using an Avid style with the clamps and the bolt holes. And I'm going to put a pin fixture system on X1, Y2. So, and I'll make like probably a 12-inch fixture system, I think. I still have to kind of figure out where I want to go with that. I might do like a Mark Lindsay bump stop and go from there. I'm not quite sure how I'm going to facilitate what I want to do there. I'm trying to see. So we've got different setups here. I showed you the different kinds of setups, and I explained a spoil board is just a sacrificial board to be able to hold material and cut through material. On a lot of things like the X-Carve, this is the spoil board. My spoil boards are pretty destroyed. I'm pretty rough on them just because. But one thing that you want to do is definitely figure out a fixturing system on clamping and positioning. And you also want to make a bump stop zero fixture. I recommend watching Mark Lindsay's bump stop series. And then you need to actually tram your machine first. So you need to plumb level and square the machine. Then you need to tram the spindle. And after you tram the spindle, you can then surface your spoil board. And what that'll do is that will take the actual surface and make sure that it's flat all the way across in reference to the x-axis. Okay, and that makes sure that whenever you put stuff on there that it's all the same level plane in reference. So that's where we're at with that. And go from there. And yeah, you definitely want it parallel to the gantry, John. And that's basically where we're at. So that's your spoil boards in a nutshell. Nothing spectacular. I'm actually overhanging mine and going from there. So that's that. I'm just trying to see here where we're at with everything. This is a T-track system, and go from there. That's one of the things that I find a lot of guys, whenever they use T-tracks with a spoil board, they don't inset them and solid mount them. So for me, whenever I do T-tracks, I'll actually cut in and then I'll put a secondary piece of MDF over top of the T-track that actually pinches it down. And then I'll put my screw holes in these sacrificial pieces of MDF. So that's pretty much all I've got on that. And that'll be about it. Just going through making sure that there's nothing major that I missed. And right now there's really not. here's a spoil board where parts of the machine are actually mounted to the spoil board. So the spoil board is an integral part of the machine. So if they ever cut through this and they have to replace it, they're going to end up replacing the whole machine. Now, a machine like this, usually you're going to upgrade it over time. So this will actually change. Another one where part of the spoil board is integrated into the machine, like my X-Carve and CNC for newbies and my DIY machine is not like that. It actually has extrusion base, and then MDF sits over top of it. And that's kind of the way a lot of the hobby machines, machine kits work, is they have MDF spoil boards, but they have a cross brace system underneath. A lot of the entry-level DIY wood kits, you'll find that they end up having a system a lot like this, where it's basically an MDF base for the machine guides, and then it sits on top of some type of truss table or something of that nature, and then they actually just router surface plane another sheet of MDF over top of that usually. Something to think about when you're making your spoil board is how much Z clearance you have. So for me, on the CNC for Noobs machine, I have 6 inches. So if I put a 3/4 inch spoil board on there, I lose 3/4 of an inch of my Z height. If I put 2 layers on there, I lose 1.5 inches. Okay, so I can take that down some by surfacing the spoil board, but you don't want to make it such that your clamps and stuff will pull out, okay? Because the whole purpose of the spoil board is to be able to cut through the material and also somehow mount the fixtures or the material itself to be cut. So this is one they actually use an aluminum base on some of these. That's not actually one of them. That's just a bad picture. Let's see if we can find an aluminum spoil board. This is usually the grading system underneath of the DIY kits. This is a deep 5-axis CNC. This is an extrusion-based tabletop or spoil board. Sorry. Now on these, you will actually put the material itself, or you'll put a sacrificial board underneath of the material, so that when you cut through, you don't actually cut into the bed of the router. Okay, that's really important. Same thing goes with a mill. If you're going to cut through, you need to make sure you accommodate that by putting spacers under it, put a sacrificial plate under it. I actually use the high density polyethylene cutting boards. I have sheets of that stuff, and I'll actually put cuts underneath, offcuts of that stuff underneath of my material, and that'll save my spoil boards. So we got some people rolling in here. We got Mark saying good morning. We got John saying good morning. We got John saying make sure that when you cut it, it's parallel. That makes it parallel to the gantry. He's absolutely right. We got Dre popping in saying good morning. I'm trying to find aluminum, and then we're going to talk about another type of spoil board hold down system. So you'll hear me use the word spoil board and fixture and hold down a lot of this stuff. There's a difference between the spoil board and work holding. Work holding can be on the spoil board, or it can be a separate fixture mounted to the spoil board somehow, and then that holds your work holding. Okay, this is an example of a spoil board with a fixture for work holding. Okay, so what we have, let's see here. There we go. So what we have here is, this is the machine spoil board. This is a sacrificial spoil board with what looks to have T-tracks in it. And then this is a clamp fixture with a wedge system. So these knobs screw onto bolts that are in these T-tracks, and that's how they made the zero plane or the work offset, the work coordinate offset, and then that holds the material here to be machined. So this is a fixture or a jig. This is a T-track on top of the surface board or spoil board. Okay. It's kind of interchangeable, kind of not. For the layman terms, yes, it's interchangeable. For actual machining and machining conversation, no, it's not interchangeable. And there's a difference between fixtures and jigs. A lot of people don't realize that. Okay. This is a square jig for squaring on that. Okay. Still haven't found an aluminum bed. I was hoping to see like a Shapeoko Nomad or something of that nature pop up. Okay, here's a Stepcraft. Stepcraft has an aluminum bed. They have it's all one aluminum extrusion, I think. I don't think that it's strips. I think they're actually one-piece beds. But I can't be quoted on that. And then on top of that, you put the MDF. Now there's another type. Oh, here's a spoil board system out of aluminum. But the really cool part about it is it's what we were talking about. It's vacuum. Okay, so you can apply a venturi or a vacuum pump or whatever you so see fit to actually make your own work hold down using vacuum. And that's always really nice because you don't have to. John asked if I'm mentioning cam hold down systems. I haven't yet. I'm going to. That's actually where I was going with it. So with these vacuum systems, you don't need to clamp it from the sides or anything. It actually has a full vacuum pad underneath of it that holds the material in place. If it's done right, you won't have any movement. So these are work hold down fixtures, not necessarily a spoil board, because you don't want to cut into this unless it's a piece dedicated for a certain part. Okay. This is an aluminum fixture. This is a vacuum plate. Okay. So now we start looking at push clamps and bump stops and stuff of that nature. This would be considered a work hold down feature or a work holding feature. This is a large format vacuum table. And then let's see if we can go all the way up. And see if we can find a cam system here. So this is a push system for work hold down. Notice they have the spoil board, a T-track system for work holding, and then a dog system for push clamps. Same premise can be had. Here we go. Here are cam clamps. And this is the work holding system that John was talking about. You'll have a stationary clamp back here. And then these clamps actually have an oblong elliptical cam to them. So you have your center point here, and this is further out than this side. So it's actually offset. So as you push this handle up, it's going to put more force right here. And that's called a cam system. Here you can see the push clamps in action against a bump stop on the X and Y. These are just simple hold down clamps. This is a cam clamp system being made. You can actually see here it humps out right there and then levels out here. So if you put a bolt in here and push this up against a piece of wood, it's not actually going to touch or put pressure here. It's going to put more pressure here. These are just smaller cams. You can see them in action here. And the size of the cam is based off of your offset of your work holes, your spoil board holes, your mounting holes, and the material size. So these are bump stops to set 0. These are cam clamps with a sacrificial board in here so as not to mar this. And they cam clamp here, here, and here to put pressure against these boards. Okay, here's another one. You have your 0 points and then your cams. So here's some cams mounted on a T-track system with multiple holes to be able to mount different different locations for camming. And that's pretty much it. That's all there is to it. Not super exciting. Nothing. This is one of those. Okay, here's a cool one. This is a T-track system with machine vices mounted on a long run. Okay, and that's always a great system. You guys will have to excuse the noise in the background. Those are plow trucks coming through and plowing us out. We got like 4.5 inches of snow last night. Well, yesterday into last night. So if you hear the scraping, that's what it is. But basically, here's a bunch of vices set up holding an aluminum extrusion or an aluminum tube that will get machined. So you can see the work holding and spoil boards and stuff like that, fixtures and jigs, they're often an overlooked part of the system. And when you overlook that part of the system, you're really not utilizing your machine to the best of its ability. These are low profile vices. This is a clamp vice. And a lot of these can be implemented on a router. You know, I've seen all kinds of stuff. I've seen routers cut steel and aluminum, bronze, brass, stuff like that. It's just a matter of making sure that you have the correct tooling and that your structure is solid enough to handle the speeds and feeds that you're throwing at it. That's basic 101. It's nothing spectacular, but it's often overlooked, and I don't know why. Okay, I'm going to go ahead and open it up to you guys and see what we've got here. If you have any questions, please post them up. Here is a fixture plate or work holding. So this actually is a ShopBot CNC router, and it mounts MDF right to a metal frame, and then you put another MDF over top of that and flatten it out. It's not right, it's not wrong, it works. That's the biggest thing with a lot of these, is just understanding as long as it works, it's the right way. As long as you can mount work holding and fixturing and stuff like that, then it's the right way to do it. just looking here, trying to go through, make sure I covered everything there. Yeah, there's nothing really major other than making sure that you surface it and it has a good flat surface to it, and that you have some type of understanding on how you're going to mount your work holding to it. And that's about it. Okay. Yeah, that's about it. Okay. So, I had a guy that messaged me asking about G-code and understanding G-code and reading G-code. So let me see here. Let me make sure I got, okay. So let me bring up a G-code. Desktop, done. Okay. Let me expand this out, expand that out. And share screen with you. Okay, this is a G-code, guys. This was written for a Haas VF1 or VF2 milling machine. It's an ashtray that I make out of aluminum. This is all program information. So it says what the program is. It's my ashtray .nc, which is the code form that Haas needs. It's just a simple program code. You can use TXT, TAP files, NC files. There's all kinds. It depends on what your controller wants, and each one has a format that it uses, and you go from there. So this says what the material is. It's aluminum. It's 2 inches in the Y, 4 inches in the X, and 1.5 inches in the Z. That's the rough material. The stock will be placed up with 3/4 inch parallels. That tells me how I'm going to mount it in the vise. So it'll be above the surface. That way, if anything goes wrong, you don't ruin your vise. The program 0 is X0, Y0, lower left corner. Okay. And then the Z0 is top of part. This is all the preamble to the program. We know that we have 2 operations, and tool number 1 is a 1/2 inch 4-flute end mill. Tool number 2 is a 0.75, so a 3/4 inch 2-flute ball nose end mill. And now we actually start with the program. Okay, so this is all the preamble to the program, or the program header beginning. So the header calls for a Haas, it actually calls for a tool change first. M6 T01 Then you have your M00. Okay. Uh, then this line tells me that this is operation 1. This is the pocketing for the center of the pocket. So my ashtray is such that you know what an ashtray looks like. It has a pocket, and then it has a holder for, in my case, a cigar. Okay. So now we move into, this is a rapid movement from X0, Y0 over to X 1.0392, Y 1.0392. Okay, so that basically puts me right in the middle of the pocket. We do a G0. Now, these G0 movements are what are called rapid movements. That means it moves over to those places as fast as the machine can move. Okay, you have G0 movements and you have G01 movements. This is the spindle on clockwise. So M3, M4 for the Haas is spindle on clockwise, and M4 is spindle on counterclockwise. And then this tells you how fast the spindle needs to move. So in my case, the Haas is moving at 2,500 RPM with a 1/2 inch bit. So now we're going to feed down 10 thousandths, and this is going to be a slow 1 inch per minute feed down. So it moved over real fast, moved down real fast, about an 1/8 inch above the material, and now it's going to slowly drive down into the aluminum material. Okay. So that's that code. And now we don't need to repeat this G01 until it changes to a G0 rapid movement. So now it's down inside the aluminum, and it's going to start cutting in the X direction by 15 inches per minute. So it's going to move 15 inches per minute to the positive direction, and then it's going to go from there to positive X, positive Y. And then it's going to go back into Y, still positive, but it's a backwards movement, X, backwards movement, and then Y, it'll be a positive movement, or that way. So an easy way to remember positive and negative movement direction is your right hand. Positive Z, positive X, positive Y. Okay, so milling machines are like that. That's the easy way to remember it. I'm just going through this code looking. I've said it a couple times. To me, looking at this G code, especially when it's playing through, is a lot like that part in the Matrix where the guy's telling Neo to look at the code, and oh, there's the blonde. You know, he can see the blonde because she's just binary numbers, zeros and ones, like in a certain order. Same thing here. I'm looking typically at like the G0 movements and the G1 movements, and I'm looking at the Z changes. Those are really the things that I key in on whenever I'm looking at G code, whenever it's running. So this is a pretty easy G code. You can actually write your G code by hand, and I've done that before, where I've written like a macro by hand and then put it into the program just using text file or Excel file. Excuse me. So let's see what this G-code looks like in what's called a simulator. This is a simulator. This is a G-code simulator. It's called NC Viewer, and it's ncviewer.com. And basically, you just go up here. This will put out your G-code, and it will actually simulate it over in this area. And you can put all your different digital readouts and all your machine options. Everything like that. So we'll open up Ashtray, plot it. Okay, now we're going to run through this. And the nice part about running through this is you can actually go right to here. Let's shrink this down. And you can play right through your G-code. And you can see where it's actually going to take place. So these are your forward and backs, and this will tell you your movements. So right now, we're actually over here. We need to zero the machine. So this will tell us where we need to zero the machine. And then it'll run through everything that we use. So this is just plotting out our machined pocket. It's not giving us the material outside or anything like that unless you have that designed in your part. This G-code didn't have it designed in the part. We didn't need it. Now, I see something that I don't like. We're right in here. I can actually back this up line by line, and then I can go in and edit that G-code. Maybe okay, so here's a Z movement. So we do a clearance, a G00, Z01, 0.1. So that takes it up to a clearance height about an 1/8 inch above the aluminum, giving the coolant the ability to push underneath the tool and clear out the chips. And then it goes to the beginning XY, and then it drops down to the original depth, and then it drops down one more time. So it goes from negative, it's moving in the downward motion, 0.565, which is a little over a 1/2 inch, and then it goes about 30 thousandths more. It's actually about 25 thousandths. So it goes down a little bit more very slowly, and then takes off at 15 inches a minute again. Maybe I want to change that, or I want to dwell this down and not keep it up. I can go in and modify just that line. So we could take that rapid movement out, and it won't come back up. What it'll do is as soon as it hits the X point here, it will then skip over this line, and then it will move itself right to this rapid. Right there. So it'll be down inside that block. So if there's anything in that pocket that might obstruct it, you can hit your end mill and snap it. That's why there's that Z clearance there. Okay, that's to save your end mill or your tool in general. But you know, like, you may not need that. In this case, I don't, because the step over clears that pocket out enough that I can actually dwell that down inside. I have my coolant, the pressure from the coolant and the air coming out is so high that it pushes all the chips out anyways. The only thing that Z does pulling up is give me time to flood that pocket with more coolant to cool the tool and float the chips. So realistically, that was the first iteration of the ashtray pocket program. So I ended up, I actually did a Z clearance layer by layer of 20 thousandths. So I actually, whatever my Z movement down was, I just cleared it by 20 thousandths up. Let the tool come up, get the bottom cleaned out, and the coolant flushed out. So this is a product that I use, and you can go line by line and see exactly what your tool is going to do. So what it's doing right there is it's disappearing because it's actually moving down. It's moving up and moving down. And it's just clearing out that pocket. We'll sit here and let it run through. And what I'm looking for is anything that might influence a crash or anything like that. So now, let's see here. Now we're changing operations. Okay, so right here is my coolant off and my spindle off. And then this goes to the 0 point right here. So this movement takes us to 0. That puts us at the top of the material. Now we need to do a tool change. This says M6 is the tool change macro, and I need tool number 2, which is a 0.750 2-flute ball nose end mill. Everything's cleared out. Operation 2, ashtray finger, that's where the cigar will sit. That goes to the Z clear. So you can see it moves from there and moves up just a little. It only moves it up 15 thousandths for clearance. Then it goes to the start of the finger, which is actually off of the material, and then That turns the spindle on, and this starts the feed. And it just goes back and forth all the way down. And now the program's done. And this is our go-to clearance height. And that goes back to 0, 0. And this ends the whole program. So all it is really, this is a really simple program, and that's why I chose it. A lot of people don't understand what's happening with their G-code. So the one gentleman that actually asked me what was happening, it turns out that he was post-processing in one program, and then he was importing into another program, and that was actually adding header and footer information, turning off some of his other parts of code, and he was crashing and ruining parts and tools. So, these things, you have to learn how to read them, and then once you learn how to read them, you'll learn how to edit them. And once you learn how to edit them, you can really take some time out of your programs. A dwell cycle on the finger, I was using a tapered ball nose end mill, or I was using a ball nose end mill. It wasn't tapered. But A, it's so big, and B, I wanted a good surface finish that I only went in the conventional milling with it. So I turned the spindle on clockwise, and I ran it from right to left. Okay, so I would do a streak, lift it up, move it over, come back, do a strip, lift it up, come over. Fusion has a new system called adaptive roughing I could have used, but I really just hogged out the material with the ball nose end mill. I could have went in with like a 1/4 inch end mill and really took things down, and then came in, left myself about 15 thousandths in the pocket in the valley, and then ran the ball nose in one swoop and cleared everything out. And that's actually what I ended up doing. So this whole ashtray program changed based off of running it the first time, changing my Z clearances. So I went in, I edited all of my 0 lifts, or all of my clearance lifts out of it, and left the tool down inside the pocket and dwelled, and then cleared everything. And then with the finger, I actually added in a third tool. So there's 3 tool changes where I did a 1/4 inch corn cob rougher, and I actually roughed out all of the valley first, and then hogged the material, the remaining material, with the ball nose. And what that allowed me to do was speed up the process. This whole program on the mill took me roughly 45 minutes to run the first time, and then I did 10 of them that way. I made sure the code was good, and then I went in and I started modifying the code, and I got this down to a 7-minute 21-second program by editing out, increasing the depth of cut, and changing my tooling. So at the end of it, I actually have a 4 tool change program where I use a heavy rougher. I actually use a half-inch rougher, um, center cutting corn cob, and it hogs down and to the side really, really quick and good. Um, if I had to rewrite this program, I'd probably use an adaptive tool, and I'd drill a hole. So I'd add a 5th tool change, and I'd actually just add a drill hole, and I'd drill like a half-inch hole into it down to a certain level, and then I would just do an adaptive tool path uh, with the center cutting corn cob rougher, half-inch, pull that, and then go back in with my 1/4 inch cleaning and clean out the pocket. So I got a tighter setup. But right now with three tool changes, it's not bad. With the 4th tool change, it's not bad. The 5th tool change I think might be overkill for this. Um, but it is what it is. So that's where we're at, guys. Quick, really easy lesson on G codes. You can actually go search your G code. So let's see, Autodesk. I'm trying to see. Here's a list of G code commands. I guess I should show that. This shows you a G0 and a G1, which we talked about. That's mostly what those movements were, is rapid and controlled motion. So your controlled motion is the G1s, and that says move here at this speed and go from there. The G2, G3 are your arc motions. It's a controlled arc motion. The G17, 18, 19 are your planes that you work in. The 20 and 21 says inches or millimeters. The G28 references your home. G90 recognizes absolute mode. G91 is incremental mode. These are pretty good. I've seen this output before, which is pretty good. So we have our comments, our feed rate, our spindle speed, select tool, and change tool. That's all relative to the controller. F is your feed rate, S is your spindle rate, T is for tool. Okay. That's pretty good on that one. Let's see here. Well, I know I can get the Gerbil. So Gerbil G-code commands. That's actually the Gerbil firmware. All right, these are there we go. Here's a list of recognized Gerbil G codes. The G2, the G3, Uh, I've heard mixed comments on whether or not they work. Um, some people have them working, some people don't. I don't even mess with them. I just use simple G0, G1s. That's my personal preference. You've got your dwell cycle, your G10s or your work offsets, um, your plane selects, inch, millimeter, call home, set home. Uh, this is a run homing cycle. G30, that's a predefined position. The G38.1, 2, 3, 4, 5, those are all probing. G40 is cutter compensation. G41, G42. G43, that's a probing offset. Uh, G49 cancels. Absolute mode override. Those are your work coordinates. So these are the list of different G codes that Gerbil will accept. These are your modals, your Fs, and your Ms. So Gerbil's really a simple program. It does not recognize a lot. So these are your coolants. This is your vacuum, tool change, spindle, program ends, and master program end. These are ones not supported by Gerbil. This is some really nice stuff to have, but Gerbil's not smart enough to support it. UC and Mach 3 do. They're the closest to a Fanuc style G code as any of them, and I really like that. These commands run homing cycle. That's the big one, is run homing cycle and turn off $X, turn off alarm. These are all the G codes. So like this is a macro. Yeah, those are all macro based. But this is all stuff that you should have in parentheses in the top part of your program. Let's see. Right here, this is all stuff that you should have in there whenever you're doing a program. And you can handwrite that just by putting parentheses around it. Sometimes Gerbil doesn't like it, but it doesn't really matter. But that's all stuff that I add to my actual programs, and it works out well for me. And we'll go from there. So I'll open it up to you guys. We got a few viewers in here. Nothing earth-shattering and groundbreaking today. I don't know. What else you guys need? What else you want? All right. 5, 4, 3, 2, 1. Have a good one, guys.